Dear students, up to this, in the chapter of Legendre's function, we have derived several important results like generating functions concept and orthogonal property. In today's lecture, we will derive recurrence relations of Legendre's function as it's written as part 1. So not all recurrence relations but few important recurrence relations of Legendre's function will be derived in today's lecture. Recurrence relation 1, as you can see, it is 2n plus 1 into x pn. Pn means pnx, the Legendre function, equals to n plus 1 p n plus 1 plus n p n minus 1. So we can see three different Legendre function are involved here with three different subscripts n plus 1 and n minus 1. We are starting from that famous equation using which the generating functions concept was discussed, and we differentiate this equation both the sides with respect to h. What we get minus half into 1 minus 2x h plus h square whole power, obviously minus 3 by 2. Then that expression differentiated with respect to h will provide minus 2x plus 2h equals to, in right hand side, simply for h power n we have n h n minus 1, then p n x is function of x, h is not involved there, within sigma n equals to 0 to infinite. Then in next step, what we are doing, that 2 is taken as common, cancelled with that half, and here we have minus x plus h multiplied with that negative becomes x minus h, and 1 minus 2x h plus h square whole power minus 3 by 2 is broken in two terms. In numerator we have 1 minus 2x h plus h square power minus half, and the remaining power minus 1 is taken there in denominator, equals to same right hand side. Then in next term we are cross multiplying that 1 minus 2x h plus h square in right hand side. Then in next term we are using that given equation 1 minus 2x h plus h square power minus half is equals to sigma n equals to 0 to infinite h n p n x. So using that particular relation, left hand side is converted into modified form and right hand side remains invariant. Then in next step we are expanding that sigma, as you can see, p0x plus h p1x plus h square p2x up to infinite, and in right hand side we are expanding that sigma of right hand side, and by doing that we can equate the coefficient of h power n both the sides, and coefficient of h power n is obviously obtained when, say, x is multiplied with h power n pnx, so it is x pnx. Then when minus h is multiplied with h power n minus 1 pn minus 1 x, so it's minus of pn minus 1 x. While in right hand side there are three different options from where h power n can be obtained. When 1 is multiplied with that term, so the coefficient is n plus 1 into pn plus 1 x, and when minus 2x h multiplied with plus n h n minus 1 pn x, then the coefficient is minus 2x into n into pn x, as you can observe there. And when that h square is multiplied with that term, we obtain the coefficient of h power n as n minus 1 into pn minus 1 x. And by simplifying those all terms together, finally equation 7.16 is providing us first important recurrence relation for Legendre's function. And here it's extremely important to derive these recurrence relations, as well as it's also important to memorize these. In next slide we will discuss derivation of next The second recurrence relation is given as npn equals to xpn dash minus pn minus 1 dash. That means we have derivatives of pn and pn minus 1 in this particular recurrence relation. As you can see, dashes denote differentiation with respect to x. We are again starting the derivation with same step which we utilized in previous derivation of recurrence relation 1, and we are differentiating it with respect to h both the sides. So up to this it's very much similar to derivation of first recurrence relation, and then it's nothing but that differentiation is written as x minus h 1 minus 2xh plus h square power minus 3 by 2, and with that right hand side is differentiated with respect to h easily. And then we are doing something different in this derivation if we compare it with derivation of first recurrence relation. Now we are differentiating that same equation with respect to x now. So here we have minus half into 1 minus 2xh plus h square whole power minus 3 by 2, and with respect to x we will get minus 2h, and minus half and minus 2h are multiplied together to provide h, and finally it is simplified in this form. And as we are differentiating with respect to x, so right hand side is h power n same, and p and x is differentiated as p n dash x. Now we multiply this equation 7.18 both the sides by x minus h. So we get this particular equation 7.19. Now can we find some standard relation between 7.17 and 7.19? Obviously yes, because that part of 7.19 x minus h into 1 minus 2xh plus h square whole power minus 3 by 2 is very much there in left hand side of 7.17, which is equals to that sigma. So that particular part of 7.19 can be replaced by that right hand side of 7.17, that you can see there using or combining equation 7.17 and 7.19 together. We get h into that part is replaced with that sigma. So sigma n equals to 0 to infinite n h n minus 1 p n x equals to same right hand side of 7.19. And then in next step we are expanding this sigma in left hand side, as you can see that, and that sigma is expanded in right hand side, as you can see that. And that what we are doing, we are equating the coefficient of h power n both the sides. How? That h is multiplied with h power n minus 1 there will provide us coefficient of h power n in left hand side as n into pn x, as you can see, and in right hand side when x is multiplied with that term we get coefficient of h power n as x into pn dash x, and then minus h is multiplied with that term will provide us coefficient of h power n one more time as minus of pn minus 1 dash x, as you can see. And then by simplifying that expression means it is also possible that you can avoid writing that x. So it's written as npn equals to xpn dash minus pn minus 1 dash is known as equation 7.23 is known as important second recurrence relation for Legendre's function. So it's about deriving two important recurrence relation in this particular lecture, and there are 4 more recurrence relation pending where these two recurrence relations are important to memorize. In next lecture we will discuss derivation of remaining 4 recurrence relations of Lagrange's function.